last speaker is going to be joining us remotely due to some travel issues. Aaron Gu received his Master of Science degree in Sports Analytics and Technologies from Loughborough University in the UK. He's currently in the PhD program at Loughborough in the Machine Intelligence Lab. His research interests include sports analytics and machine learning. So hopefully he'll be on the screen very shortly.
It's working.
Okay, I think we're good.
Yeah, should I start right now?
Yep, you can start.
Thank you. Thank you very much, Mark, for the introduction. Also, I really want to thank you before I do the presentation because of the help for trying to let me to attend this conference. I'm really grateful, and I'm really honored to have this opportunity to share my research with the experts in this area. And yeah, let's start. So the topic of my research, the topic of this research is contextualized generative ghosting model as benchmark for evaluating player movement in football. So before I start talking about the detail of this research, I want to just have a little bit introduction of myself. So Mark has already mentioned I'm the PhD student in Loughborough University, and my research mainly about using machine learning techniques to analyze big data in soccer, so to gain the insights which can be used to help the coaching staff make better decisions. The below is my bio and the LinkedIn link. So as we all know, the current analytic models in soccer have basically covered the current analytic models in soccer have the expected goal model and expected possession value model, also the VAEP model, and these models have some similar features, like they are all supervised learning methods with defined input and output. And also their model performance is heavily relied on the distribution of the training data, and they need a huge data set and to make the model training successful. And also in specific game possessions, their model can hardly be used to answer the what if questions. When we talk about what if questions, actually it means like in a certain situation we want to know what other teams will do in a similar the game context. We wanted to have a comparison between this team performance with the other possibilities, and this kind of features kind of limitation to this current state-of-the-art analytic models in soccer. So our model, generative ghosting, can be used to answer the what-if questions. I will talk about the details in the following slides. And this is a method, it's a combination of unsupervised learning and supervised learning. And it's more likely to capture the generative patterns within the data we use to train the model. And this kind of pattern can be used to build a benchmark, which can be used to analyze the real performance better. So this is basically the overview of this research and the intention of this research to solve the gap between the current research and the purpose of this kind of football analytics, and try to solve the problem, to answer the question about the coaching stuff, help them to reach better decision-making in the game plan. Here is some background information, the background knowledge from the previous papers we used in this research. First one is a deep generative model on time series data. And this kind of model is usually applied in processing the videos and images or the voice data. So as shown in the slides, if we use this method in a certain scenario like this, trying to model the one person's body motion when he's walking, jogging, and running, and if we have the images of this kind of person movement, we can use the model to extract the information of the the body movement to the latent space, because the input data can be very high dimension. And latent space can be an extraction of the input data, and that can capture a lot of information, contextualized information from the input, and which then can be used to reconstruct the input. So the reason why this is kind of useful in our case is because if we imagine we are not treating, we are not dealing with the body motion input data, we are dealing with the football data. So football data is always very high dimension because we have 22 players and one ball. The trajectories can be really complicated. So we can use this kind of method to extract the information to latent space and to reconstruct it, which can help us to do a very strong prediction. As you can see in the right-hand side of this slide, if we we have the input as a body movement, we can, for example, if the current time step, we have a body like stay still or like work very slowly. And if we have a trained deep generative model, and we can use it to predict if it's gonna work or keep working or start jogging or start sprinting in the nighttime step, what will happen, what the body motion or what the image will look like. So we can do the similar stuff in the football. So if imagine if we have a certain possession, we have a certain time step, we can kind of train this kind of model and can to predict the future. So we give some kind of labels, and this kind of prediction model will help us to generate the future, which can be used to analyze the real football game. So this is the reason why we use this generative model to train our deep generative ghosting. I will talk about ghosting in the further slides. So before jumping into that, there's another very important knowledge which is used in this paper. This is the pitch control. This has been introduced by William Spearman in 2018. It's a very famous model in this area in football analytics, in the soccer analytics. So this is in the left-hand side, is the players' positions on the pitch. And you can see the red dots denote the attacking players, and blue dots denote the defending players. And the right-hand side is what is generated by the pitch control function. So what happens is the pitch control use the statistics and physics to capture the features of the players and generating this kind of possibility map, which denotes, for example, in the red area means the area controlled by the attacking team, and blue area denotes the area controlled by the defending team. So the calculation of whether this areas belong to each side is based on the position of the ball, position of the player, and also the speed of the player, the players and ball. So the calculation is made, and this kind of heat map can be generated. And there's a lot of information included in this pitch control or heat map. So you can see, we can not just see the players' positions, we can also see their space controlled by each team. So this space is very indicative, because in the football, if you wanted to score a goal, you need to utilize the space. So the space very important in creating more chances. Now, if you're stuck in the middle, we don't have the space in the two side area. It will just prevent to create more space and increase the scoring chance. So this is the logic of this model, and we gonna use this pitch control function and to process our data. I will talk about it in detail in the following slides. So the generative model and pitch control function are two important things we used in our research. So first, the data we use have two parts. First is event data, and the second is tracking data. So they are from professional soccer matches. And because we are in collaboration with several football clubs, so we got the data, but this data has the confidentiality, so we cannot to share the exact names, the team's names, or players' names, but I will just talk about it. And yeah, so the event data actually is that, for example, if you see a football game, there are passes, shots, dribble happen in this game. So for each event, we have the information like what time this event happened, or where this event happened, which player is involved in this event. All this information included event data, but the event data is not enough because it's discrete data. It's not continuous. If you see in the gaming, it's every second we need the tracking data. So tracking data actually captures the information of the players' trajectories, all the players' positions and ball positions for every given time step. And with the tracking data and the event data, we can literally have everything included every data included in a football game. So as I mentioned, this kind of data can be really high dimensional, and this kind of high dimension data will be really hard to deal with when we train the machine learning models and we're trying to gain some insights. We need to try to downsample it and make it easier to analyze. So the way to processing this kind of high dimensional data is the pitch control function. So we use the pitch control. It's not to just directly convert the data and to analyze the pitch control map. Otherwise, we use the pitch control function to extract the information from the high dimensional data and to convert the previous tracking and event data to this kind of images. So for given game context, we have a pitch control image, a heat map, instead of the high dimensional tracking trajectories and event information. So we have these images, and our model is going to be trained on these heat maps instead of the trajectories and event information. So after processing the data, we train our whole model in two parts. So the first part is we try to train a deep generative model, which is used mainly for the prediction. So if you can see the upper left, so the left-hand side is the input sequence of heat maps, input sequence of pitch control maps, and we extract the information from this input, and then we reconstruct that from latent space to the output. And this model, after trained, we can use it to predict the pitch control maps. So for given game context, for example, T0, we can predict the heat maps in T1, T2 in the following seconds and use this generative model. And this kind of prediction can then be used to train our deep generative ghosting model. So if we have the heat map predicted, we wanted to know what the player actually positioned on the pitch other than only know the area. So we train another model. So it's the part 2. We train another convolutional neural network. So we have the input as this heat maps. We have the output as the player positions, and we use the when the output player positions can use the statistics and to reconstruct the image. And that thing, the difference between the reconstructed image from the player's positions and the real input can be used as a loss function to train this convolutional neural networks. And after we train it successfully, we can use this kind of images, we can generate the player positions. But one thing to mention, these player positions cannot be really accurate, because if you see that there is a possibility within that, it's not like a deterministic process. So we can possibly have like kind of a player prediction. The player position can be a little bit, have some randomness, but still a very limited in the area, which is according to the loss and according to the training is successful. And we're happy about that. I'm going to show you the result of the trained model, the power of that in terms of analyzing the football games in the following slide. And this slide shows how this whole deep generative ghosting model works and how it's constructed. So this one is without the ghosting, like each player position involved, but this shows the prediction model. I mean, the deep generative model in terms of predicting the area changes, show how it can work, can be used in the real life to help the coach making better decisions. So this slide is to show how to use the prediction model to help the coaching decision. But the second slide will show you the deep generative ghosting, how the player actual positions can help. So I will play the video. And this video can help us to understand how the model works in terms of helping the team and to improve the player performance. So if you see this position, so it's a attacking team gain the ball possession and try to start a counterattack. And in the middle show the predicted heat maps and the real heat maps. And the right-hand side show, so we use a matrix, we use a matrix called expected position value, the EPV. The blue charts show the real possession, and prediction is shown as an orange line. So this line it's a metric called EPV, expected possession value, to evaluate the position. So we use this metric to quantify the prediction and also the ground truth. And if you can see in this possession, the blue line, so it's higher than the prediction line, the orange line, so which means in this possession, the real team performance outperformed the benchmark, which is a good possession. So if you can to play the video again, we can see it in the real life broadcast footage. The white shirt, the attacking team, they start the counter-attack really fast. And the reason why they make it successful is because they utilize the wing space very good. The left side wing and right side wing, it can also be seen in the real pitch control maps. And this is not happen in the prediction heat map. So the reason why the line, I mean, the blue line is higher than the orange line is because of the wing space created lots of value. And this is addition. So this is much better than the prediction. So in prediction, you can see in the average team, maybe just do this counter-attack without fully utilize the wing space, and which might be a cause why this in real life position they successfully scored a goal instead of losing this chance. So this is how we can use our deep generative model as a computational benchmark to analyze the football game in terms of analyzing their utilization of space. And for the next slide, I'm gonna explain how can we use our deep generative ghosting, so this exact predicted player movement, and to analyze the football game. So if you see in the previous slide, we can only, from the human perspective to annotate when the space control is different, when the heat map different, how it looks like, and we need a lot of human labor, a lot of human work, but we want to actually to let the coach directly see the result without personally to annotating, because it's really time consuming, right? We are trying to build a benchmark to help them to reach the decision faster and more efficient. And so after we train this deep generative ghosting, we'll have a very direct indication to the coach what is really happening in the match and what should really happen in the match. So if you see these slides, in the first row is the broadcast footage. This is the same possession as the previous slide show. So this possession, and in the mid row is the real possession, what it looks like in terms of the heat maps. And the third row is the ghosting possession. So including every ghosting player's position, movement, trajectories, and also their heat map. And if you can see that from the fourth column, in the real possession, so in the real possession, in the fourth column, in the real possession, the left wing side is covered. You can see the red area is marching towards the opponent's goal. But in the ghosting possession, is not like that. The reason why it happens, if you can see, maybe it's a little bit smaller dots, not easy to detect. But so if you see, let me just try to zoom. Let me try to zoom this. So if you can see, so in the real possession, this player's position is closer to the opponent's goal. So he's really sprinting faster than the real, than the prediction and the benchmark. So in the prediction, this ghosting player, it falls a little bit behind. He's still trying to utilize the space and trying to run forward, trying to create a chance for the teammate, but he's not running that efficient in terms of covering the space closer to the goal. So this directly just have very big impact in the game, because if you are the defender, if you see this player like moving that's very close to our defensive line, you need to be aware of that. You need to cover that space, which help the other teammates in the middle to have even more space, because the teammates are trying to utilize the space in the wing area, which just help really important movement. Is even though he doesn't receive the ball, but he still creates a space, which is very crucial to the success of this possession. And also, if you see the other player in the right area, in the right wing area, this striker, this guy, in the real possession, he's running towards the side of the defensive line, and he's trying to create a space in the right wing. And what happened in the prediction, in the benchmark, he just stuck in the middle. He's trying to stay in the middle because this guy, his starting position is in the middle, and the prediction, so predict in the average league performance, average player in this situation will just running forward, but will not just will not running to the right-hand side of the defensive line, trying to utilize the right wing space. It's not very detectable at the beginning. So, but in the real possession, what happens is this guy is really makes very good decision making in terms of utilizing right wing space. And what happens if you see the last column? Last column. Sorry. So what happens is if you see the final column and this number 9, so this right is located in the right wing side. He has a huge space in front of the goal, also in the right wing, and the defender is all attracted by the other player. And the left wing side is also creating the spaces in the left wing. And both these movements are really important because the ball handler have a huge space in front and he can have plenty of time to make decisions whether to pass each of the player because the defender are all attracted by this kind of off-ball movement. So what happens is this ball handler finally passed the ball to the right-hand side to this striker who utilized the right wing area. And this guy finally scored a goal. If you can, let's just look at this real footage again. So this is the place. So this striker number 9, he is utilizing the right wing space, and then he received the pass, and he scored a goal. So with our deep generative ghosting, so we can compare the real possession, the real player movements with the ghosting player movement. And the power of this is we can do this kind of calculation, how far you are from the prediction, whether you outperform the prediction or you underperform the prediction according to the scoring chance created in a given possession. So with our deep generative ghosting, we can not only analyze the team performance in terms of covering the space, we can also analyze the individual performance in terms of the contribution to the space created. So this helps us to have an evaluation metric, utilize our build benchmark model, and to evaluate every individual's performance in terms of the covering the space and running to the open space and creating a chance for the teammate. Even though he's not receiving a pass, he's still making contribution to the game. So this is very important for us to be more precisely, more objectively to evaluate every player's game performance and to let the coach to know who is to outperform the benchmark, who is doing very well, who is not very well, even though he scored a goal, maybe he's not creating enough chances as expected according to our benchmark. So this can be a very strong tool for doing this kind of analysis and help the coach to make better decision making. So in conclusion, our deep generative model can be used as a benchmark, so evaluate the soccer player performance on the pitch. This model can be used to analyze the team movement and individual players' ability of utilizing the open space. So, but we have some limitation in our research as well. So, because right now we still focus on the space creation. So in the end of the world, we still need to consider about more directly, how it contributes to the final scoring chance, because we have expected goal already, have already mentioned by previous researchers. So we can combine our deep generative ghosting with the expected goal model or even more statistical model, combine this both, and to utilize the whole, to utilize our trained ghost and also statistics metrics, and to analyze each player, each movement, each decision-making, each pass, each dribble, his contribution to the long-term goal, which is the scoring. And this is going to be really important to the match analysis and can be used to help the coaching staff to just make more data-oriented decisions. So that's it. That's my research. Thank you for listening. Any question is really welcome, please. Thank you. Thank you, Mark.
Okay, thanks. Are there any questions for Aaron that I can relate to him? Yep. Actually, you know what? Hold on. We have these guys here. Listen.
Hi. I'm Alex. I'm a student at Boston University. So I'm wondering, when you compare the predictive model to like the real-time possession model, did you find that like the predictive model would under-evaluate like the real scoring chance, or that it would over-evaluate it, or it kind of fluctuated and so it matched the training data?
Do you mean when we train a model, how the model is, how the model performed in comparison to the real data? Do you mean that?
Yeah, like on the slide where you were comparing frames, like the real
Yeah.
scoring chance. Did you find that when you looked at situations that the predictive model, like in the case you showed, it kind of or the real like chances of scoring, I guess we'll say, was higher than the predictive model? Did you see like a trend in terms of like over evaluation or under evaluation?
Yeah. Yes, so actually, so if I understand correctly the question, so when we train the model, we try to focus on push, the prediction or the reconstruction closer to the real input data. So when we train that, we didn't try to let the model to outperform or underperform it. We try to let it to the prediction to as close as possible to the real input data. So we try to build this kind of model and to represent like a league average performance, because we're training on a lot of games, and it's like we will try to use this kind of prediction model, try to predict like what's most likely, by the average team in a league to perform in a given context, and when in a new testing sequence, and we just use our model and to do the prediction, and we try to compare the new testing performance with this trained model's prediction performance, and to see whether it's underperform or outperform. Does it answer your question?
Yeah. So, yeah, when you were comparing the predictive model that you got from the training data, and you compare that to the testing data, did you find that like situations matched, like overall, like it was accurate?
Yeah.
Okay.
Let's do one last one, because then I think we have to break. You can email Aaron.
Yeah. I email. If you have any questions, please drop me an email.
One more.
Hi, this is Alex Fairchild. I work for Arsenal as a data analyst. What I really like about this is that run made by the winger is how you would coach a player to move in that moment to create a 2v1 against the fullback. What my question is because the ghosting model predicts the movement would come to the inside, what I like is that this shows the difference which you're trying to show between the movement. But is this movement that the ghosting model predicts based on the movement of the specific player in that specific moment, or is it based by team? I guess what I'm asking is, what's the sample that's predicting the movement in that moment?
Thank you very much for the question. Yeah, I think it's a very good question. And this is not solved in our research, because when you mentioned, when we make this kind of prediction for each ghosting player, do we have the identity of the player? We don't. Whether he's moving, like that as a winger, or like a fullback, or like a midfielder, we don't have this kind of entity implemented in the training. So that possibly, like we should improve our model in the future in terms of adding this kind of identity, like the role of player to this training data. So will possibly help us to reach better results. But it's very, very good question and very good suggestion as well, because we haven't covered this yet. Thank you for the question. And I think we will get improved in this perspective as well in the future. I think it's a very good direction. Thank you.
Cool. Thank you.
Let's thank Aaron once more.
Thank you. Thank you very much.
Aaron, thanks you so much. And I'm sorry we couldn't have seen you in person today.
Thank you very much for the help, Professor Mark. I'm really grateful to your help, to be honest. Thank you.
You're welcome.
Hopefully see you one day in Harvard. Thank you.
Sounds good. I hope so too.
Thank you.
All right, and so we're now ready for a break. We have an hour for lunch. Aaron, you can take longer if you want. Actually, I think it's dinner time for you.
Yeah, it's dinner.
So, and then we'll just reconvene at 2 o'clock, again, in Science Center D and Science Center D. Center C and D. Okay, see you in an hour. Okay, thanks again, Aaron. We'll be in touch.
Take care, Mark. See you.
All right.